So welcome everybody to our Gamma seminar. Today we have the pleasure to case Oscar Carballal from the Department of Algebra, Geometry and Topology at the Universidad Complutense de Madrid. He's going to talk about mixed superposition rules and compatible geometric structures. So Oscar, thank you very much for accepting our invitation. It's a pleasure to have you here, and the floor is yours.
Thank you, Javi, for the introduction. And as you said, well, I'm going to talk about mixed superposition rules and compatible geometric structures. And this is a joint work with my PhD advisors, Ludwig Campromor Sturzberg and Francisco José Ranz, and also with Javier de Lucas. So this talk has several different parts. First of all, I will talk something about Lie systems, right? I think, well, a lot of people here for sure not about Lie systems. And then I will talk about a somehow generalization of the concept of superposition rules for Lie systems, which is known as mixed superposition rules. So roughly speaking, the main idea of mixed superposition rules is to allow, in the general definition of a superposition rule, the particular solutions to belong to maybe different systems, right? Not only to consider just solutions of the same system. Then I will talk about Dirac Lie systems, that is, Lie systems compatible with Dirac geometry, and also show how the so-called coalgebra method can be applied in order to derive mixed superposition rules for Lie systems in a somehow algorithmical way. And finally, I will comment an application of our theory to thermodynamics. So first of all, just let me start with Lie systems, and of course with the somehow canonical example, which is the Riccati equation on the real line. The Riccati equation on the real line is the following first order differential equation in normal form, where these functions here, v0, v1 of t, and v2, are just time-dependent smooth functions. And although the expression of this OD, which it is in normal form, is quite simple, I mean, it is polynomial, in general, it cannot be solved by quadratures. It can if the time-dependent function satisfies certain condition, but somehow that is a bit restrictive for applications. But although we cannot express the solution of the Riccati equation by quadratures, we know that if we have four different particular solutions, namely x1, x2, x3, and x4, their cross radio, when regarded as affine points of the real projective line, is constant. And the cross radio is this expression here. And let me say that it is constant equal to a certain real number k, right? From this expression of the cross radio, we can express, for instance, any of these four solutions, let me say x1, in terms of x2, x3, x4, and this constant k, right? And the importance of this expression is that it is not only valid for x1, but for almost every solution of the Riccati equation. That is what we call the generic solution of the Riccati equation. And in a few minutes, I will talk about somehow more precisely about what is this generic solution thing. Okay, so this is, well, the first example. And now our objective is to formulate, using differential geometry, these ODs, right? So the first point is, how do we describe these ODs using differential geometry? Well, that is through the so-called time-dependent vector fields. A time-dependent vector field on a smooth manifold M is just a smooth map X from R times M to the tangent bundle of our manifold M, such that this diagram here is commutative, where the arrow here from R times M to M just stands from the projection onto M, onto the second copy, and the arrow here from the tangent bundle of M to M just stands for the projection of the tangent bundle. And the commutativity of this diagram is, well, you may equivalently regard X as a section of the pullback bundle of the tangent bundle through this projection, right? That is the same saying that this diagram commutes. Or equivalent, maybe this is useful for in practical situations, is that a time-dependent vector field X is just a t-parametrized family of usual vector fields on M. And these vector fields xt are just obtained by fixing the time t in the coordinate of R. So associated to a time-dependent vector field, we have the so-called associated system of ordinary differential equations, which is this system of ordinary differential equations, and it is in normal form. So in the stack, I will only consider systems of ordinary differential equations in normal form, and we have a one-one correspondence between these systems and time-dependent vector fields. So I will use X to denote both a system and its associated time-dependent vector field. So now the idea is, okay, we know how to describe these non-autonomous ordinary differential equations, but well, what is now a superposition rule? Let us say depending on L particular solutions. Well, a superposition rule is then just a time-independent map phi, which is defined from L copies of our manifold M and another extra copy onto M. And the dash arrow here means that this map is in general only locally defined. So it is defined on a certain open subset of this manifold, right? And its image is a subset of M. And it satisfies that the generic solution xt of our system X can be cast in the following form, right? In this form, where x1 and xl are is a generic family of particular solutions of our system X, and K is a point of our manifold which is related to the initial Cauchy problem of our system X. Okay, so back to our Riccati equation, the superposition rule reads as follows, right? In this way. It is this map psi, well, psi node, phi, sorry. And we have these three particular solutions, x2, x3, and x4, right? And our point K belonging to the real line. And previously I said that this is only locally defined because, more precisely, this map phi is defined on the open subset of R3 times R, where these 3 points are different, right? And this denominator here is non-zero. So what is the thing that we can only recover almost every particular solution of the Riccati equation? Well, if in this expression we set k equals 0, we recover the x2 solution, right? If we set k equals 1, we recover the x4 solution. And finally, if we set, let me say, k equals to infinity, we recover the x3 solution. And this means that a global superposition rule, this means that all particular solutions of the Riccati equations can be recovered only if we consider k equals infinity, and this means the one-point compactification of the real line, okay? So in general, if we consider only this superposition rule defined on the real line, we can recover almost every solution of the Riccati equation. So this is somehow what is called a local superposition rule, and I will just consider local superposition rules. Okay, is there any question so far? Nice, I will continue. Okay, so a Lie system on a manifold M, it can be defined in several equivalent ways, but I will say that it is just a time-dependent vector field on our manifold M, which takes values in a so-called Béziot-Goulver Lie algebra. And a Béziot-Goulver Lie algebra is just a finite-dimensional Lie algebra of the Lie algebra of vector fields on our manifold M. And for X to take values in V just means that it contains this family of vector fields, okay? And as you can imagine, a time-dependent vector, well, a Lie system may admit several, even non-isomorphic Béziot-Goulver Lie algebras. So a very natural question now is, okay, how do we know if a given system of ordinary differential equation that's admit a superposition rule? And we have a characterization, which is originally due to Lie, although in modern geometrical terms, it was proved by Carignana, Grambowski, and Marmo. It is the so-called Lie theorem, and states that X admits a superposition rule if and only if it is a Lie system. So back to a Riccati equation, we know that.
Oscar, just one remark
Yeah.
about this theorem. There is another theorem between these two groups of guys by Ogijevic and Grunland, and they made also a Lie system theorem for PDEs, but you know, as a particular case, it gives the case, the ordinary one. But it's I mean, the Lee is the original, the Kariņģena-Grabovski is very formal, and Grunland did, well, something in between, let us say that, in that manner.
Okay. Thank you, Javi, for the remark. That's true. I mean, sometimes I forget about that result, but it is indeed also very interesting, and for sure there are a lot of work by Grunland in these PDE systems. So thank you. And well, let me continue saying that we know that the Dirac equation admits a superposition rule. So by Lie theorem, it must be a Lie system. And for sure, this is the case because the time-dependent vector field x associated with the Dirac equation reads in these ways. And it can be decomposed as a function b0 depending on time times a vector field x1 plus a function b1 depending on time times a vector field x2, and the same with v2 and a vector field x3. And these three vector fields x1, x2, and x3 have the following commutation relations, these ones here. And this means precisely that they span a Béziot-Goulbert Lie algebra V, which is isomorphic to SL2R. And remarkably, this Béziot-Goulbert Lie algebra arises from the local Lie group action of SL2R, which I denote in this way, on the real line by Möbius transformations. Okay, so just let me comment some approaches to Lie systems theory. The first one is through local Lie group actions, and a very deep result due to Palais states that every Béziot-Goulbert Lie algebra can be integrated to a local Lie group action, just in the case as in the Dirac equation. This theory was somehow initiated by Béziot while studying systems of partial differential equations, in particular the so-called Darboux integrable PDEs, and several people here has worked on this approach. For instance, for the case of homogeneous spaces, of Lie systems on homogeneous spaces, we can find some works by Winternitz and the CRM school, also including Harnad and so on. Also some works by Kariņģena and Ramos, also with applications with control systems theory, and for instance also by Dubrov and Komrakov. In the framework of complex algebraic geometry, we have very important results due to Blázquez, Sanz, and Morales, also with applications to the so-called, how was this called? Galois differential theory. And there are also examples of how Lie systems arise while studying initial value problems for Darboux integrable PDEs. And you can find some results about this in the book by Stormark and also in a paper of Ian Anderson and Mark Fels. Well, a very striking point in Lie systems theory was by this foliation theory approach to Lie systems by Kariņģena, Grambovski, and Marmot, as Javi said previously. And one remarkable property of this approach is that it allows to consider somehow Lie systems compatible with several geometric structures. And this is the second line I want to comment.
Oscar,
Yeah,
because when I talked to Winternitz, he knew about this, about the foliation approach, but he didn't want to use it because he was more focused on applications and classification theorems, because he was doing this big program about classifying all systems related to primitive transitive Liages. I think that was the proper name.
Mm-hmm.
But he didn't develop it because he was not so much mathematical like Kariņģena, Grabovski, and Armo. But he pretty much knew all the main ideas, because there is one paper, at least, I don't remember where, he explained more or less this thing, yeah, because indeed it is in the proof by Lie is indeed in the using this foliation theory approach, but it's pretty much implicit. Let us say that Kariņģena, Grabovski, and Marmot did it in full, yeah, in a full manner, but the idea was previously already know the works.
Yeah, that's true. Thank you, Javi. And yeah, the point is in also some papers. Maybe, well, this is late by Dubrov and Konrakov. There are similar ideas, not using the foliation in the language of Kariņģena, Grabovski, and Marmot, but yes. So the second line about compatible geometric structure, which somehow originates from this Folliesian theory approach by Kariñena, Grabowski, and Marmo, is to make a Bessiot-Gulberly algebra compatible with a geometric structure. And this means that this Bessiot-Gulberly algebra consists on infinitesimal symmetries of a given geometric structure, right? Roughly speaking, in general lines. And for applications in mathematical physics, what we look for is for Hamiltonian vector fields. For instance, in the case of symplectic geometry, or maybe Poisson, Jacobi, Dirac, which will be the case of this talk, and also maybe like for contact, K-contact, and a lot of possibilities. For instance, in the case of Poisson geometry, there is the so-called coalgebra method, which was developed by Ballesteros, Serranz, Cariñena, De Lucas, and Sardón. And through this approach, it is possible to obtain superposition rules somehow algorithmically, which is interesting for practical examples. Also, the approach to Dirac geometry, which is originally due to Cariñena, Grabowski, De Lucas, and Sardón. The multisymplectic geometry approach due to Gracia, De Lucas, Muñoz Lecanda, Vilariño, Roman Roy, and Rivas. And recently, the K-contact approach due to De Lucas, Rivas, and Sobchak. So as you can see here in these slides, we have a non-trivial intersection. And just finally, other approaches and generalizations of Lie systems include representation theory, for instance, Lie systems on curved spacetimes, quantum groups, PD Lie systems, as Javi said previously, also supergeometry, which is due to Winternitz and collaborators, stochastic systems, etc. So you can make somehow Lie systems appear wherever you want. And now, just let me comment some references. The standard ones somehow are this book by Javi and Cristina Sardón, this publication here due to Cariñena and Javi, and also maybe these lecture notes by Pavel Winternitz. Okay.
Oscar, just one comment. When I talked to Winternitz, there was something that I used to call Winternitz motto, and he said that wherever you have an integrable system, you have a Lie system.
Yeah.
He had no proof of it, okay? But he said something like, if you have something that looks like integrable, some Lie system is behind it. And pretty much worked. So that's partially why they are everywhere. As you said, you can find its applications and relations to many other things, many other fields. Thank you.
Yep. So now, just let me introduce mixed superposition rules, okay? So the main idea of mixed superposition rules is, okay, for the case of a Lie system and this standard superposition rule, we have to take particular solutions belonging to be particular solutions of the same given system. And the main idea now is, okay, can we change the particular solutions and consider particular solutions of possibly different systems? And the answer is yes. And the most classical example is an inhomogeneous linear system on Rm of these four, n times n real-time dependent matrix, and B is a time-dependent vector field on, well, not time-dependent vector field on Rn, but a vector on Rn such that its components are smooth functions depending on time.
A curve on Rn, yeah?
Yeah, a curve on Rn. Yeah.
Yeah.
Thank you.
By the way, just one thing. This is the easiest example about this mixed thing. But the truth is that when we did this, Grabowski and myself, the original thing, it was back to Winternitz again. And it was something called the Milne-Pine equation of the Yermakov system.
Mhm.
There are different names, but they are related between them. And there was a way of describing the solutions of a Yermakov system, of a Milne-Pine equation, sorry, that is an oscillator with a centrifugal term, essentially, in terms of an harmonic oscillator. And we ask ourselves that if in this case the Milne-Pine equation that was proved by Whitney, that is a Lie system, and the ordinary oscillator that was two copies, if I'm not wrong, I don't remember exactly.
Yeah, two
Was
copies.
it was again related to a list system if there
Mhm.
was some general theory, and it was a general theory. Of course, after that, when we presented this to the public, yeah, the easiest way of presenting the idea is this system. But the original thing, it was in papers by Winton, and indeed he has lots of examples with lots of ideas, and they are not developed. This is just one of them.
Yeah. And for instance, apart from this, for the case of this Milne-Pin equation, Yermakov equation with centrifugal terms, so on, you can also prove, for instance, that whenever you have an harmonic oscillator, you can describe the general solution of the harmonic oscillator in terms of solutions of a certain Riccati equation, right? So this is, for instance, another example. And back to this inhomogeneous linear system, okay, we know for sure that the general solution of this system can be expressed as a particular solution of the inhomogeneous system plus the general solution of the associated homogeneous system, which is just this system here, okay, without the curve. And this means precisely that we can express the generic solution in this way, where x0 is a particular solution of the inhomogeneous system, and this thing here is just the generic solution of the associated homogeneous system. So we have n different particular solutions of the homogeneous system from x1 to xn, and also these initial conditions here, which is just a point on Rn. So the question now is, as Javi said, under which conditions the generic solution of a given system X on M can be expressed in terms of a generic family of particular solutions of possibly different systems, let me say X1 to XL, and some constants related to initial conditions. Formally, this is what is known as a mixed superposition rule, and I will just say that a mixed superposition rule for a system X on a manifold M in terms of some systems X from X1 to XL on certain possibly different manifolds, M1 and ML, is just a locally defined map, which is defined from the product of all the auxiliary manifolds and our manifold M onto M, through which the generic solution of our system X can be expressed in terms of a generic family of particular solutions of the auxiliary systems and some constants on the manifold M related to initial conditions. And as in the case of standard superposition rules, we have the natural question whether when a system does admit a mixed superposition rule. And the answer is this theorem, which is due to Grabowski and Javi, and it states precisely that a system X admits a mixed superposition rule if and only if it is a Lie system. Okay? So mixed superposition rules are valid for sure for Lie systems, and that is the case. But a priori, one can consider different systems to construct the mixed superposition rules, which may be non-Lie system. Okay. So some examples of mixed superposition rules are, as I said previously, inhomogeneous linear systems, and we can describe the generic solution in terms of the associated homogeneous linear system, and also the so-called Riccati hierarchy. And we can, in this case, describe the generic solution in terms of homogeneous linear ordinary differential equation. And two references are the following papers. This is the one of Grabowski and Javi, which includes the general theory about mixed superposition rules and all the examples of the Riccati hierarchy, and also our preprint about these mixed superposition rules and how to make them compatible with certain geometric structures. So in this paper here, we had two big questions. The first one was, well, is it possible to recognize remarkable families of Lie systems that admit in somehow a natural or canonical mixed superposition rule, such as in the case of inhomogeneous linear systems? And the second question was how to formalize, how to make them, how to describe in a very algorithmic way through the coalgebra method the mixed superposition rule and how to obtain it. Sorry. So now just let me recall how does the mixed superposition rule arises geometrically. So let me say that we have a system X on a manifold M, and we have our auxiliary systems X1 to XL in our manifolds M1 to ML. And we consider now the so-called, oh, sorry, this slide was previous. Well, in order to describe mixed superposition rules geometrically, we need to introduce the so-called direct products. In general, if we have, let me say, L vector bundles, E1 to AL, which are vector bundles onto manifolds M1 to ML, their direct product is the vector bundle over the product of the manifolds, right? Whose projection is just the product of the projections of these vector bundles, and it is equipped with the fiber-wise vector space structure on the fibers, right? So here. And well, it is not difficult to see that this direct product of these L vector bundles can be identified with this Whitney sum, okay? So the direct product is just the Whitney sum of the pullbacks of the vector bundles. And in particular, these identifications show that, for instance, the direct product of the tangent bundles equals to the tangent bundle of the direct product, as one can expect. So before going into how to describe mixed superposition rules geometrically, we need to see how can we mix these different systems, right? And this is precisely the notion of direct product of time-dependent vector fields. And provided that we have L time-dependent vector fields on these manifolds, its direct product is the vector field on the time-dependent vector field on the product manifold, which is defined in this way. So we fix a time t, we pick a point on the product of the manifold, on the product manifold, and then the time-dependent vector field on this point is defined in this way, which this thing here is just the direct product of all the vector fields, the time-dependent vector fields. And a useful notation for what follows is the following. If we have a single vector bundle E onto a manifold M, the direct product of this vector bundle with itself L times is what is called the diagonal prolongation of the vector bundle, right? And in particular, if we have a Bessiot-Gulberly algebra on a manifold on this manifold M, we will denote in this way the Bessiot-Gulberly algebra on the product manifold with L copies of M, and which is spanned by the so-called diagonal prolongations of the vector fields of this Bessiot-Gulberly algebra, right? And of course, this thing here is isomorphic to B. Okay, so this is just a notation I will use in what follows. So once we have introduced these direct products, we can describe mixed superposition rules geometrically. And now we can go to this slide. Okay, suppose that we have a system X on a manifold M, and we have these auxiliary systems, Xi, on these manifolds. Let me say that we have L of them. We now consider the direct product of all these time-dependent vector fields as defined previously, and consider also the smallest Lie algebra containing these vector fields. This Lie algebra spans a generalized distribution on the product of all these manifolds, which is denoted in this way, okay? And we denote the projection from the product of M and all the auxiliary manifolds onto the rest of the auxiliary manifolds by dropping the first M manifold in this way, okay? And the following theorem by Grabowski and De Lucas states precisely how to characterize a mixed superposition rule geometrically. It says that our system X admits a mixed superposition rule in terms of these auxiliary systems if and only if the restriction on of the tangent map of this projection, which drops the initial manifold, when restricted to the generalized distribution, is injective at generic points. And generic points of these distributions just mean points where the rank of the distribution is locally constant, and they form an open and dense subset of the manifold. And remarkably, locally, this implies this condition here, okay? Assume that X admits a superposition rules in terms of this system, so this map is injective, and X takes values in a Bessiot-Gulberly algebra, and this implies also, in a somehow topological sense, the existence of a locally defined submersion, which I also denote by this dash arrow, from the product of M and all the auxiliary manifolds onto M, satisfying the following two conditions. The first one is that the generalized distribution, okay, which was spanned by this vector field here, okay, is contained in the integrable distribution which is associated with this submersion. So the kernel of the tangent map of the submersion. And also the second condition is that the fibers of the projection dropping M are complete transversals of the foliation defined by this submersion psi. Geometrically, this can be sketched in the following way. We have our subset D of generic points of this generalized distribution, okay? And we have the projection onto the product of the auxiliary manifolds, and the situation goes as follows. There is somehow a 1-1 equivalence, 1-1 correspondence, let me say, between these mixed superposition rules in terms of these fixed auxiliary systems and local inverses of this map. Because the conditions for the submersion psi such that the fibers of the projection are complete transversals of the foliation determined by psi imply that this map here is a local diffeomorphism. So we can talk about local inverses of this map. And indeed, whenever we have a local inverse of this map, we have a mixed superposition rule. And when we have a mixed superposition rule, we can construct, at least locally, such a submersion psi. Okay? And the geometrical situation is that, okay, we have the submersion psi, we pick a value k, okay, on the manifold M, and then we consider the fiber through psi. And this describes a leaf, okay, at least locally, of the foliation. And the point is that when we consider a fixed point k, this fixed point k in M, then this map here, the graph of this map parameterizes in this way, this leaf of the foliation, right? So this thing here. And as we see here, we have that the fibers of the projection dropping the manifold M are complete transversals of the foliation determined by the submersion. This means that if we want to determine a mixed superposition rule, what we have to do is somehow to determine constants of motion of the vector fields of this distribution, time-independent constants of motion, and then consider the situation when they define such a submersion psi. Okay?
Uh,
Yeah.
just one comment. Can you show the previous slide, please?
Yes.
Okay, see, this theorem Grabowski, Janus, and I did, it is the natural generalization of a condition to say whether a Lie system admit a standard superposition rule. In the case of x1, xl are the same. The thing is that the initial condition that we generalize in here, it was a gap in the standard Lie systems theory, the Lie theorem, which says when first order differential equation in normal form admits a superposition rule, and this condition was missing in many proofs of the Lie theorem. It didn't appear, and so there was a paper by Grabowski, Marmo, and Cariñena when they stressed this fact very heavily, saying that this was missing in the literature. That's as I said it was. I mean, the difficult thing was to do what Janus and Marmo and Cariñena did, and in this case it was not easy, but it wasn't difficult. Okay, so
Yeah.
this is the story behind this theorem. I remember that I did it and then discussed it with Janus, but the original idea, the hard stuff, was at the beginning. Thank you.
Thank you, Javi, for the remark. So yes, the main point is that this result, well, at least for me, is shows that clearly that this submersion exists locally and is somehow the object you use to obtain a mixed superposition rule. So now, just let me say that, well, as I pointed out previously, we were looking for families of Lie systems which somehow possess a mixed superposition rule in a natural way, as in the case of inhomogeneous linear systems. And we found two of them. The first one is that of imprimitive Béziot-Gulberly algebras, and I must say that it is somehow very geometrical. And the second one will be that of semidirect sums, which is more algebraic. So first, just let me talk about these imprimitive Béziot-Gulberly algebras. Prior to this, just let me recall that a Béziot-Gulberly algebra is said to possess a modular basis if it admits a basis which is formed by linearly independent vector fields at generic points. In particular, this implies that it admits a basis which is linearly independent over the ring of smooth functions on our manifold M. And also that if we have a Béziot-Gulberly algebra which possesses a modular basis, every basis of the Béziot-Gulberly algebra is modular. So now we say that a Béziot-Gulberly algebra is said to be imprimitive if there exists a regular and integrable distribution D on our manifold M, such that the Béziot-Gulberly algebra acts as Lie symmetries of this distribution. And this distribution will require to be proper, meaning that it does not coincide with the tangent bundle of our manifold M. And to act as Lie symmetries means precisely this condition here, that whenever we pick a vector field of the Béziot-Gulberly algebra V and a vector field which is tangent to the distribution, a section of the distribution, the Lie bracket is again a vector field which is tangent to the distribution, a section of the distribution. So now we must assume a somehow regularity condition, which is that the foliation defined by this regular and integrable distribution is simple. This means, more concretely, that the leaf space of the foliation is a manifold, which in general does not hold globally, locally yes, but general no, and that the projection onto the leaf space is a submersion. In this case, one can prove that we have the following exact sequence of Lie algebras, okay? And this thing here is just the projection of the Béziot-Gulberly algebra onto the leaf space, which is a manifold. And here we have the vector fields which lies in V and are tangent to the distribution. So a natural question now is, can we express the general solution of a Lie system X which admits this Béziot-Gulberly algebra in terms of particular solutions of the projected system? And in this case, how many solutions do we need? And the answer is the following theorem, which says precisely that we have two cases. The first one is when the Béziot-Gulberly algebra does not contain vector fields which are tangent to the distribution. And somehow this means that when we project the system, we don't lose information, somehow. And in this case, we prove that X admits a mixed superposition rule depending uniquely on L particular solutions of the projected system. When this L is an integer such that the diagonal prolongations of the projected Béziot-Gulberly algebra to the product manifold of L times, this thing here, possess a modular basis, okay? That is, as I said previously, a basis which is formed by linearly independent vector fields at generic points. And the situation when the Béziot-Gulberly algebra contains vector fields which are tangent to the distributions is not that good. In that case, we proved only that X admits a mixed superposition rule depending on particular solutions of X and also particular solutions of the projected system. And moreover, what we also prove is that in the case that the smallest Béziot-Gulberly algebra containing the vector fields xt, this familiar here, contains vector fields which are tangent to the distribution, then our system X does not admit a mixed superposition rule dependently uniquely on particular solutions of the projected system, meaning that in this case we also need for sure particular solutions of the original system. So this is the first family, which is, as you can see, very somehow geometrically. And sorry. And the second one is that of semidirect sums, which is more algebraic. And the setting is the following one. Assume that we have a Lie system X, which possesses a Béziot-Gulberly algebra, which is a semidirect sum in this way, okay? And here V1 stands for the subalgebra and V2 for the ideal. And we want to define the part of our Lie system X which takes values only in the subalgebra V1, and this is not difficult to define. It's just the unique time-dependent vector field Y on our manifold M, such that for every t, it belongs to the subalgebra V1, and the difference between xt and yt lies in the ideal for every t. So this precisely means that we can decompose, if you want, with this thing here lying in V1 and this thing in V2. And this. And what we prove that is that in the case that we have a Lie system which possesses a Bessel-Gulbert Lie algebra which is a semidirect sum, then we can obtain a mixed superposition rule for our Lie system X in terms of particular solutions of X and Y, where Y is the part of X taking values in the subalgebra V1. Okay. More precisely, we need S particular solutions of X and L particular solutions of the part taking values in the subalgebra V1. And precisely these integers, S and L, are such that for the case of L, that the diagonal prolongations of the subalgebra to L copies possess a modular basis, and for the case of S, such that the diagonal prolongations of the ideal to S copies possess a modular basis. So these are somehow the two families we have identified. And well, I will give an example of all these results at the very end of the talk. Is there any doubt or question so far? Okay. So now what I will introduce is Dirac geometry and how to make Lie systems compatible with Dirac geometry, obtaining the so-called Dirac Lie systems. And then we will talk in the point 4 of the presentation about the coalgebra method and how to apply this Dirac geometry to obtain mixed superposition rules. Okay. So first of all, just let me say something about Dirac geometry. First of all, just let me consider the generalized tangent bundle of a manifold M, which is the Whitney sum of the tangent bundle and the cotangent bundle of our manifold M, and equipped with the following two structures. The first one is the following symmetric pairing, which is defined as follows, such that the pairing of a vector field X plus a 1 form alpha and a vector field Y and a 1 for beta is just 1/2 of the first form evaluated on the second vector field plus the second form evaluated on the first vector field. And the second structure is the so-called Dorfman bracket, which is defined as follows. We pick a vector field X plus a 1 form alpha and a vector field Y plus a 1 form beta. And the Dorfman bracket is the Lie bracket of the vector fields X and Y plus the Lie derivative of beta with respect to X minus the contraction of the differential of alpha with respect to Y. And this bracket is, for instance, satisfies the Jacobi identity, but is not skew symmetric. Equivalently, you can define all these things about Dirac geometry instead of working with the Dorfman bracket, working with the so-called Courant bracket, which does not satisfy the Jacobi identity, but it is skew symmetric. And these Dirac manifolds were introduced by Courant in this paper here. So precisely, we say that a Dirac manifold is a pair M and L, where L is a vector subbundle of the generalized tangent bundle of M, satisfying two conditions. The first one is that L it is a Lagrangian subbundle with respect to this pairing here we have defined, this one here. And the second condition is that L it is involutive with respect to the Dorfman bracket. And well, this can be equivalently defined by considering the Courant bracket instead of the Dorfman bracket. And some examples are, for instance, per-symplectic manifolds and Poisson manifolds. And this is because if we consider in general two form omega in our manifold M and a bivector pi, this determines morphisms. In the case of the two form, a morphism from the tangent bundle to the cotangent bundle by contracting with vectors. And for the case of the pi vector, a vector bundle morphism from the cotangent bundle to the tangent bundle by contracting with covectors. And their graphs of these morphisms are Dirac structures if and only if, for the case of the two form, if it is closed, meaning that it is a presymplectic form, and for the case of the bivector, if it satisfies that the Schouten-Noyes bracket of pi with respect to itself is 0, meaning that it is a Poisson bivector. So presymplectic manifolds and Poisson manifolds are particular examples of Dirac manifolds. More concretely, some relations relative to standard inclusions of some geometric structures are the following ones. For instance, every orientable contact manifold, let me say M and eta, is a presymplectic manifold by considering the differential of the contact form. Okay, and every presymplectic manifold is for sure Dirac. Also, every symplectic manifold is presymplectic and in particular Dirac. And also, symplectic manifolds are also Poisson, which are also Dirac. And for instance, also we have that orientable contact manifolds are Jacobi manifolds. I will not talk about this, but they are Jacobi manifolds such that the associated rep vector field is nowhere vanishing. And such Jacobi manifolds are also Dirac. So these are some relations relative to these standard inclusions. Okay, so now in order to make Lie systems compatible with Dirac geometry, we have to talk about dynamics on Dirac manifolds. Okay, generalizing Hamiltonian dynamics on symplectic and Poisson manifolds, for instance. So first of all, whenever we have a smooth function on a Dirac manifold M, we say that it is L admissible with respect to this Dirac structure L if there exists a vector field xf on M, a so-called Hamiltonian vector field associated with the function f, such that xf plus the differential of f is a section of the Dirac structure. And, well, an important observation is that an L admissible function may admit several Hamiltonian vector fields. And an important property for the case of constructing mixed superposition rules is that, as in the case of symplectic and more general Poisson manifolds, we have a Poisson algebra structure, but not in the space of smooth functions on the manifold M, but on the space of the so-called L admissible functions. Okay, and the Poisson bracket is defined in this way. We pick two L admissible functions, say f and g, and their Poisson bracket is just take a Hamiltonian vector field associated with the first function and then take this Lie derivative of the second function with respect to this Hamiltonian vector field. And this definition for sure does not depend on the choice of the Hamiltonian vector field associated with f. An important property of this space of L admissible functions is that whenever we have a finite family of L admissible functions, just let me say f1 to fr, and we pick a capital F a smooth function from RR, to R, then this composition is again an L admissible function. This property here allows to prove the following property I will comment. And the setting is that suppose that we have a morphism of Lie algebras where G is a finite dimensional real Lie algebra onto the space of L admissible functions. Okay, then we can define this associated moment map, which is a smooth map from our manifold M onto the dual vector space of the Lie algebra G, which is defined through contraction as follows. We pick a point of our manifold M, then we consider also an element V of the Lie algebra, and then this thing here, which should be an element of the dual of the Lie algebra evaluated on V, is just consider the smooth function on the manifold M associated with the element V of the Lie algebra and evaluate this function at the point X of the manifold M. And this map, which is the so-called moment map associated with this morphism of Lie algebras, is smooth. This implies, in particular, that we can consider its pullback, which is a morphism from the dual space, well, from the space of smooth functions of the dual of the Lie algebra, and takes values in the space of L admissible functions. The fact that it takes values on this space is proved precisely using this point, right? And remarkably, the pullback of the moment map, it is a morphism of Poisson algebras, where the dual vector space of the Lie algebra G, it is endowed with the Kirillov constant Suryo-Poisson structure, as usual. So now, how to make Lie systems compatible with Dirac geometry? As I said previously, this was done by Kariñena, Grabowski, De Lucas, and Sardon, and the procedure is the standard one, okay? More specifically, we say that a Dirac Lie system is a triple which is formed by a manifold M with a Dirac structure L and a Lie system X such that it is a Lie system on this manifold M, which possesses a Bézier-Gulbert Lie algebra V consisting of Hamiltonian vector fields relative to the Dirac structure. Provided that we have a Dirac Lie system, we can prove that there exists a finite-dimensional Lie algebra H of the space of admissible L functions, such that this Bézier-Gulbert Lie algebra consisting of Hamiltonian vector fields is precisely formed by the Hamiltonian vector fields associated with the elements of this finite-dimensional Lie algebra of L admissible functions. And the application to somehow superposition rules is that, okay, assume that we have a Dirac Lie system, consider this finite-dimensional Lie algebra H, and say that it is isomorphic to an abstract Lie algebra G. This can be done, for instance, by considering just a basis of H. And then define a morphism of Lie algebras phi from G to the space of L admissible functions by the choice of these bases. And that is, we can construct this morphism of Lie algebras satisfying that its image is precisely H. Then, using that the pullback of the associated moment map it is a morphism of Poisson algebras, we have that whenever we have a Casimir function on the dual space of the Lie algebra, then the pullback of this Casimir function it is a constant of motion of the Lie system X. And this is precisely the relation which allows to construct a constant of motion for Dirac Lie systems in general, okay? And by a Casimir function, I just mean a function here such that it Poisson commutes with every element of the dual of the Lie algebra. Or equivalently, that the associated Hamiltonian vector field is 0. So now our objective is how to describe these mixed superposition rules using this theory of Casimirs and so on. And this can be done using the coalgebra method. So just let me recall very quickly what is a coalgebra. The definition of a coalgebra can be summarized through the commutativity of these two diagrams here, okay? The first one just states that the algebra is associative, and the second one that we have a unit element, okay? So what is a coalgebra? It's just somehow you pick the definition of an algebra through these commutative diagrams, and what you do is you reverse the order of arrows. So for the multiplication of the algebra, what we have is a map which goes from the tensor product of an algebra A with itself onto A, and for the coalgebra, it is a map which goes from the coalgebra C onto the tensor product of C with itself. And we also have this co-unitality condition, but for our purposes, it is not that important. And precisely, a Poisson coalgebra is just a coalgebra which is endowed with a Poisson bracket, okay, such that the so-called coproduct, which is, just let me say, the opposite arrow of the multiplication for the case of an algebra, it is a Poisson algebra morphism. So now the idea is that we can introduce these coalgebra structures to construct this constant of motion for the case of Lie systems using the previous Dirac geometry, and this is done as follows. From now on, G will be a finite-dimensional real Lie algebra, and well, the space of smooth functions of its dual vector space is a Poisson algebra relative to the Kirillov constant Suryo bracket I commented previously. I must say that, well, there were some inaccuracies in the literature saying that this space here is a Poisson coalgebra relative to this Poisson bracket, and some people consider this a certain coproduct which goes from this space onto the space of smooth functions of two couple of the dual of the Lie algebra defined in this way. But the point is that this coproduct here does not take values in this full space here, but in this subspace, which consists on finite sums of smooth functions of each of the copies of this tensor product. In order to solve this problem, what we did was to consider a bit of functional analysis, and indeed, this space here is a so-called nuclear and Fréchet space, and as that, it has a topological tensor product, which yields a canonical isomorphism in this way. Okay, and for our purposes, what this implies in general is that whenever we have smooth manifolds M1 and N1 and M2 and N2 and smooth maps F1 and F2, then the completed tensor product of the pullbacks equals to the pullback of the product of the smooth maps. So
Oscar, yes, one remark. Every physicist knew that somehow this must be the case. But in the sense that intuitively it should work. In several of my first papers, we used the symmetric algebra indeed to avoid this. In other papers, physically it is allowed, but I have to recognize that you were the first who explained the exact mechanisms where this is work. I found something like that in a work with a guy that it wasn't never published. Indeed, one day we can talk about it, and maybe you want to finish it because it's almost finished.
for sure.
In that paper, something about this was done, but I recognize that your method is the most elegant one to do so. So I have to confess that it was, for the first time, it was written really properly. Yeah. So that's the only thing I wanted to say.
Thank you, Javi. Yeah, that is true. I mean, formally, the previous theory in physical examples and so on works perfectly. But the point is that the mathematical precise theory is this one, using these nuclear and Fréchet spaces. So the real structure we have behind this space is that of a well-behaved topological Poisson coalgebra. This means precisely this. Just look at this diagram here. The coproduct now is just the pullback of the multiplication, which is just the usual addition of elements of the dual vector space. Okay, just the vector addition. And the point is that using that this multiplication here is associative, what we have is that this diagram here commutes, and this is precisely the same as the co-associativity of a usual coproduct in a coalgebra, but the point is that the usual tensor product is replaced by the complete tensor product, and what we have now is that the structural maps of the coalgebra are continuous in the Fréchet topology. And this coproduct can be generalized to a higher order coproduct somehow by taking several compositions in this algorithmic way. Okay, this is just somehow a bit technical and rudimentary, but for our purposes, I just want to show how all these things can be applied to a very concrete example, which I think it is much more illustrative. Okay, we will consider the thermodynamical phase space, which is R5, with the so-called Gibbs one form, which is this form here. Okay. And by thermodynamical phase space in these 5 dimensions, I mean that we have two kinds of variables. We have extensive variables, which are denoted by U. This is the internal energy, S, which is the entropy, and this V, which is the volume. And we have also the so-called intensive variables, which are the temperature, T, and the pressure, which is P. And the Gibbs one form reads as follows. And it satisfies this condition, meaning that it is precisely a contact form. Okay, and we will now consider the following list system, right, on this space, which is given by the following first order system of ordinary differential equations. depending on 6 time-dependent functions from big 1 to big 6, and this forms means precisely that somehow it can be decomposed in terms of a system for the extensive variables, which is linear. So the general solution of this system here, which is in blue, is just obtained by taking three particular solutions and linear combinations of them. But the case for the intensive system, that is the one which is in red for the temperature and the pressure, is much more difficult because it is in a particular case of a so-called projective Riccati equation. And although we know how to obtain a superposition rule for this equation, what we will show is that using this Dirac geometry and coalgebra method, we can obtain a mixed superposition rule for the intensive system in terms also using particular solutions of the extensive system, the linear one. Okay. So the 6 vector fields of our system reach as follows in these coordinates, and they span a Bezier-Gulberly algebra, which is a semidirect sum of SL2R and R3. This means that we can apply the theory of mixed superposition rules and semidirect sums. Now the question is, how do we derive compatible geometric structures with this system, turning into a Dirac system? And this can be done as follows. We take this Lie algebra V prime of this Bezier-Gulberly algebra, which is spanned by x1, x3, x4, x5, and x's, and is isomorphic to the semidirect sum of B2 and R3, where B2 is just the barrel subalgebra of SL2. And remarkably, the generator satisfies this condition here, meaning that their wedge product is nowhere vanishing whenever the entropy and the so-called Gibbs free energy, which is this smooth function here, it is non-zero. Indeed, if we have a particular solution of this system, then the Gibbs free energy reads as follows, and a similar thing for the entropy. This means that if we have a particular solution such that the Gibbs free energy of the entropy are zero, then they are equivalently they are constant, right? This means that we can restrict to this open submanifold where both the entropy and the Gibbs free energy are non-zero, and where the elements of V prime constitute a so-called locally automorphic Bezier-Gulberly algebra. This means that the dimension of the Bezier-Gulberly algebra equals the dimension of the manifold, and the generalized distribution spanned by this V prime equals the tangent manifold of M. This means that this vector field here form a frame of the tangent vector. So, in the case of locally automorphic Bezier-Gulberly algebras, we know that the space of least symmetries formed by those vector fields which commute with every vector field of V prime is indeed a finite-dimensional Lie algebra, and also isomorphic to V prime as a Lie algebra, that is, to the semidirect sum. In particular, when we pick a basis of this Lie algebra of symmetries, it yields a dual coframe on this open submanifold M, given by the following 5 one-forms. And this one-form satisfies, as one can expect, the Moret-Cartan equations of this Lie algebra, which is isomorphic to V, isomorphic to V prime, isomorphic to the space of symmetries of V prime. So now, this can be used to derive a geometric structure for the whole Bezier-Gulberly algebra V, as we will show. Whenever we consider a one form alpha, which is a linear combination with constant coefficients of this one form, it is a one form which is invariant for V prime, meaning that the Lie derivative of alpha with respect to every vector field of V prime is zero. Okay? In particular, when we pick the whole Bezier-Gulberly algebra V, this one form alpha is invariant for V if and only the coefficient phi3 is 0, and the same for the fourth coefficient, which goes with this one, with alpha 4. This yields the following expression for alpha. In particular, such alpha is a contact form on M if and only if C1 and C5 satisfies that their product is non-zero. And remarkably, if we pick C1 equals to C5 equals to -1 and C2 equals 0, we obtain this form here, which lies in the same conformal class of the Gibbs one form, and it is a contact form. Okay? And with respect to this one form, to this contact form, we have that our original system is a Dirac system relative to the presymplectic structure induced by the contact form. Okay. So the associated Hamiltonian functions of our original vector fields are the following ones relative to this Dirac structure, and they span a Lie algebra which is isomorphic again to SL2R semidirect sum with R3. With respect to the Poisson bracket on the space of L-admissible functions, which are just those functions which are first integrals of the x6 vector field. And remarkably, this vector field here is just the rep vector field of this contact form eta, which is proportional to the Gibbs one form. Okay. And in order to apply the coalgebra method, we pick our morphism of Lie algebras defined by these Hamiltonian functions, and we use this Casimir function of this Lie algebra, right? Where the V's have the same commutation rules as this A.
Oscar,
Yep.
one question. In thermodynamical system, most important subspaces are those where the denominator of these functions are equal to 0. What do you do in that case?
In the case where the Gibbs free energy is 0, you mean?
Yeah.
Well, in particular for the case of this system, what we have is that if we have a particular solution so that its Gibbs free energy is, vanishes, it is equivalently, it is constantly 0.
Mm-hmm.
So
Yeah, but geometrically, can you do something on this space? Because it's a very important subspace, yeah? And essentially, what you're saying here is that the formalists, the Hamiltonian functions, they are not defined there. So a natural question is to think what is going on in that subspace. Maybe you can do some kind of reduction or whatever. Uh,
yeah, I think so. I think so because precisely, if I remember correctly, the this vector field here, which is the rep vector field of eta, it is a symmetry of the whole Bézier-Goulverly algebra, right?
yeah.
And this means that, yeah, I think you can perform this kind of reduction.
Yeah, but another thing, this red vector field, yeah,
Yeah.
okay, of the symmetry. Mhm. Can you show me again the R6?
If maybe I'm mistaken, Javi, but I think it was a symmetry because this Lie algebra has not.
Symmetry. Yeah, it's well, in that case, it's you because here there are many morphisms that you are dealing with it.
Yeah.
Yeah,
Mm,
indeed, the X6 is what is called a gradation. Yeah, generalized vector fields of degrees. And what it's saying is that you as an new, there
mhm,
are coordinates with values equal to 1, remaining ones are equal to 0. And so you can work out the commutator of that with the other things. It's pretty much easy. Because, for example, with x1, the
mhm,
first term has you up and down, so the total degree is 0.
mhm,
Second, 2, 3, t is equal to 0, up and down, so it's 0, p equal to 0, so commutes. And
mhm.
you can do similar stuff with other ones. For example, x3, nu has degree 1, u has degree 1, but it's down, so the total degree is 0.
Mhm.
P is equal to 0, so commutes with x3. With x4, doing the same stuff, commutes
Yeah.
with x2, doing the same stuff, yeah, commutes to with the last one, commutes to with x4. If you are the degree a gradient here, it's pretty
Yeah.
much easy to see the x6 commutes with all the remaining vector fields. So
Mhm.
yes, it is a symmetry. And the thing is, when you have the eta, yeah,
Mhm.
you want to make the reduction, the standard reduction, you have to make the contraction of x with eta, yeah?
Yeah.
And this x gives you, and with eta, how much, what does it gives?
Okay, the contraction of eta with
With
x6.
x is 1, yeah?
Yeah, minus, I mean, yeah, the red
Minus
vector. Yeah.
1. Yeah, it's the minus. Okay, so you have this Hamiltonian function, but the problem is that, well, it's not regular at all. So you have your first problem.
Mhm.
And okay, I mean, the general stuff doesn't work pretty much.
Okay.
Probably. Oh, it was the first thing. There was one. It will be all the space, and you have to reduce. Well, you should take a look at it, but
Okay.
I
Okay.
could take a look at it very carefully to check whether everything works. Because here, well, there are other ways of doing this,
Okay.
but that is interesting to look to study this some manifolds, the reaction and properties, because indeed you
Okay.
are removing something that it is a subspace that is maybe one of the most important things in the model. So I
Okay.
could
Okay.
take care of
Thank
it.
you. Thank you. I will take a look. Thank you, Javi.
Mm. And talk with Adam. Maybe he can tell you something about it.
Okay. Sure. Sure. So, well, back to our example. I was just saying that if we have this Lie algebra morphism with this Casimir function, we can produce, it can be used to produce this mixed superposition rule, which reads as follows. It is indeed a mixed superposition rule for the intensive system, written in terms of three constants, okay? One particular solution of the extensive system, which is the linear one, the easy one. Then one particular solution of the extensive system with constant entropy. The thing that we are considering constant entropy means that we are applying this result of imprimitive Reshod-Gould-Berle algebras. And finally, one particular solution of the intensive system, which is associated with the Levy factor of this decomposition. And here we're applying the result on semidirect sums. And it precisely is that part, it is this system, okay? This one here. And just in order to end, just let me recall some conclusions and further work. At least for me, the most interesting thing to go further will be study PDEs. Okay, and for instance, we know that the general solution of this Liouville equation can be expressed in this way, and this kind of expression is known as a superposition formula for this Liouville equation. And also, there is a hierarchy of PDEs, the so-called Darboux integrable PDEs, which were proven to admit this kind of mixed superposition rules by Anderson, Fels, and Vasiliou. And some ideas will be to characterize general families of
Jest
PDEs.
16:30.
Sorry? Will be to characterize partial differential equations admitting mixed superposition rules in order that we generalize Lie theorem and Darboux integrability. And maybe in terms of morphism of Pfaffen vibration and the relating relative algebroids in the sense of a recently developed theory by Smildy and Rui Loya Fernandez, and also using the pseudo groups of symmetries and Lie algebra shifts in the sense of Juan and Acornero, two PhD students of Marius Kreinig. So this is all. Dziękuję bardzo, and thank you for your attention.
Thank you, Oscar, for a nice talk. So, is there any question, comment, remark? Nothing. Well, I made my questions already. So the thing is, take a look at that. It could be.
Well, I always make the same type of remark of questions, but so but I think it's important that when you consider contact dynamics, that
Yeah,
the contact Hamiltonian vector fields do not depend on the specific contact form, but on the conformal class or on the distribution.
I agree.
So how does that affect all these Lie systems?
Well, Asier,
Sorry.
I didn't. Well, in general, the point is as the examples I know in practice. I don't know if Javi, if you know some of them which do not work. I mean, which work in the non-orientable case.
No, I don't even say I mean,
Okay,
it
okay.
can be orientable, but
Yeah, okay. Yeah, yeah,
the particular one form is
sorry.
just a representative in an equivalence class if you
Okay,
want, but the final results shouldn't depend on the representative.
Yeah, these vector fields here, as here, the original ones before deriving the Dirac structure, are not only, well, you can imagine, they are also Hamiltonian vector fields relative to the Gibbs one form. So yes, they are symmetries of the contact distribution for sure, of the original one. I don't know if when you have given the Schott-Gulberly algebra formed by contact Hamiltonian vector fields, meaning that they preserve the contact distribution, if at least locally you can always find some contact form lying in the same conformal class such that they commute with the rep vector field. I don't know. I don't think so, but does
Once again,
this
could you repeat the last thing? Because I mean, the fact that they are Hamiltonian is something that does not depend on the contact form. It's just that they preserve the kernel, so it doesn't matter. The only thing they do is that they relate these contact vector fields with certain Hamiltonian functions. This is the only thing the eta does. It's a representation. Yeah, it allows you to talk about the Hamiltonian formalism because it matches every vector field, contact vector field with a Hamiltonian function locally. This is one thing. So independently of the eta, if you have these liabilities, they will be exactly the same in all the representations. That doesn't matter. The morphisms, the algebraic morphisms, they will be the same. The only difference is that the functions that they will be defined in this thing. And does not really depend. I mean, if you have certain kinds of manifold or whatever, it's not important. Another thing I can tell you is that in thermodynamics with the form, yeah, when you have a contact form, you have
several representations? Yeah.
Yeah, you have 30 representations, but it's much better to think about geometric stuff about it. So one is the kernel. One other thing is isotropic submanifolds. Another thing is coisotropic submanifolds, Legendrian submanifolds, and things like that. And it turns out that in certain cases, problems that appear numerically with your functions, they are related quite probably, if I don't remember with Legendrian submanifolds that are very relevant here. So
they are the equilibrium configurations, in fact, I think.
Yeah, and it's the thing is it could be interesting to check what is going on in these cases and to see what happens with these particular submanifolds because they are maybe even the most important with respect with certain aspects. And everything works. I mean, the problem and what it does not work probably will not work with any other representation. But it's something that it should be studied. I mean, the problem is that when you use a particular eta, everything is up to that. And you have to say what is going on always. Yeah. So try that. I mean,
it will be interesting for sure. Yeah.
Yeah. I mean, it's something could be nice. And well, there are all the stuff, for example, we did with Adam, and it was with it was not contact, it was K-contact, it was with hydrodynamical systems, the spin hydrodynamical, thermodynamical systems. And it could be also interested to check what is going on in this systems. So you can generalize some of this stuff to this case. So this is much interesting than this, yeah.
But in that case, you have PDEs, right?
You should have PDEs in that case.
Okay.
You have sections and related with certain problems, with pseudo gauge and all the stuff. So it would be interesting to generalize what is going on in those cases, too. There are more things you can do. So, it's something that you can try.
Yeah.
And for PDEs, K-contact PDEs, I think that we did it with Thomas, yeah? Thomas, we did it at the very end, yeah, in the paper?
Yeah.
Yeah, so I mean, you could try if you can study mixing what Thomas did and what Adam and Mikhail we did together. So it could be interesting to check it out. Yeah. So this is
Okay.
the thing.
Thank you.
You're welcome. Any other comment, remark? So thank you again, Oscar, for your nice talk. It's been a pleasure. And send us the slides, please.
Okay.
Upload
I will.
it. Julia, please stop the recording.